Time doesn't matter between now and the start, but so I'll just go ahead and start it up now. And
we're all happy with the levels?
yes,
Okay.
sounds great. So yeah, in a couple minutes, you're good to start.
You want to maximize that on the screen here?
Yeah.
Perfect. That'll work.
Well, okay. So since he's coming in, you're going to need to use the Teams. Okay, got you.
Yeah. That's fair.
So you don't even need the PowerPoint open.
No, yeah.
I would go ahead and close out PowerPoint and anything else that you don't need open.
For speed's sake.
Correct.
Okay.
And you don't need to keep the one that I have there.
Yeah, I would make sure to just close all that out.
Okay, just open that and don't save.
Don't save. Okay.
Okay, so what do we have open?
Just Teams.
And what's the other program that's connected to Teams? Is that the calendar?
It's the calendar. That needs to stay open. But everything else is fine. No, yeah, we're good.
Okay. Can you make it large or does it matter?
I can. It's already maximized. I can hide the taskbar if that matters.
It's fine. Well, that's up to y'all. We're not in charge of the report, so that's your choice.
It's okay.
It won't record the taskbar
Okay.
anyway. It just records what's in Teams. So everything's squared away. I'm good.
All right. Sounds like we're good.
Here. All right.
Awesome.
I'll hang out. We'll be going at.
Ram, we've been giving everybody a couple of minutes to try to move from presentation room. So we'll start, at 40, maybe 47, if that's all right with you.
You're going to introduce him and then he's going to talk?
Yeah, I'm going to introduce him, then I'll mute mute all of the room and let him talk.
Okay.
I heard you. I need to mute myself because it's recording starting. Okay.
So
Okay.
who will be talking in here live? Just you?
Me, and then I'll until we have Q&A. I'll mute in here until Q&A, and then I'll unmute. And
Well, there only will be one of these, like term.
no, I'm going to mute it on here.
Oh, I was talking about these.
Oh, I don't know. Yeah.
You're not going to have a panel.
Not until 4 o'clock.
Oh.
It's not. You can keep them all on. I'm just going to mute here.
Okay. All right. My name's Aaron, by the way.
Thanks, Aaron. All right. Well, I'll go ahead and start the introduction for RAM, and appreciate everybody coming in here and the Appendix K OGI LDAR presentation breakout room. Dr. Hashmonay is an international expert in the development and implementation of optical remote sensing and other advanced monitoring methodologies. He is the co-inventor of a radial plume mapping method. It's EPA, other test methods 10 or OTM10, optical remote sensing for emissions characterizations from non-point sensors, and projects performed under Dr. Hashmonay direction for both public and private sectors. Advanced methods have been used to measure gaseous particulate emissions from sources as diverse as landfills, concentrated animal feeding operations, wastewater treatment plants, alkali plants, refueling stations, military aircraft, fugitive dust from military activities, open burning barges, near road mobile sources, agriculture operations, fertilizer manufacturing plants, oil and gas production facilities, coke oven, batteries, chemical manufacturing plants, and petroleum refineries. These field experiments provided essential data for calculating emissions factors for these sources. His methods have also been applied for emergency response as well as for human health and safety applications. Specialties for Dr. Hashmonay include advanced air monitoring solutions, especially fence line monitoring and fugitive source emission monitoring of greenhouse gas and other air toxics. Ram, I'm going to go ahead and mute us and let you take over.
Okay. Thank you for this introduction. I did not send it to you. You took it from somewhere else. It's a very long one. I would like to apologize. Good morning, everybody. I would like to apologize not being there. It's Passover, happy Passover, and Good Friday tomorrow. We stayed in Israel for celebrating our holiday here. So we have our booth in the showing room, and we have our American representatives in our booth. My talk is about critical technological review of Appendix K, and when Appendix K proposal was open for comments, we started to send our comments to EPA, and in the last round, we sent a new set of comments when we found out some pretty significant technical issues with the Appendix K, especially on the matter that there is no sensitivity criteria for the entrance of the OGI camera into the appendix, under the Appendix K survey. Last week, I had a presentation, very similar presentation at EPA to the people who are responsible for Appendix K, and they listened to me. They couldn't comment in this stage of the rulemaking, but I believe there will be some changes according to what I've showed them last week and what I'm going to talk right now. Our main issue is with the response factor. Response factor
Ram, it looks like you've muted yourself somehow.
Okay, now can you hear me?
I can now, yes.
Okay.
And the slides are moving.
Yeah, I moved the slide, but it's not moving with the space bar or the arrow. I need to. Okay, I'll continue. So our main issue is with the response factor, and the main reason, if you can read from 1.2 scope of Appendix K, which is supposed to be a protocol to do surveys, LDAR surveys with optical gas imaging. In the definition, in the scope section, they already put in the response factor, and they said that 75% of by volume of the compounds needs to be 0.25 response factor. What I understood from EPA and from my discussion with other people is what they really wanted to say, that this filter needs to be between 3.2 to 3.5 micron, where all of these VOCs, relevant VOCs that are we are supposed under the new regulation to find in LDAR survey overlap in this spectral region of the OGI filter, bandpass filter. So we, up front in the scope of the Appendix K, they're saying 0.25, and they don't say here that it's 0.25 and 10,000 ppm. The factor needs to be at a specific concentration, because the response factor is a curve, is a function of the CL value. So you can see here, and the only paper they rely on is the Zhang et al. 2017, that is about the development of the response factor. And this graph is from Zhang et al. And you have the curve of the response factor as a function of CL, the ppm meters. And you can see the vertical line here is the 10,000 ppm meters, and you can see where it's crossing each one of the compounds. The lower one here is methane, and they decided, since the 0.25 is slightly lower than 0.3 that they got, 0.978 or something like this, that they got for methane at 10,000 ppm meter. So they determined that the threshold for the response factor will be 0.25 at 10,000 ppm meter. But what is very important to understand, this is response factor, which is a ratio of the response of methane to the response of propane. And you can see here, right now, propane is not in the list because it will be a straight line at 1. But here in the wording of the scope, they said when compared to the response factor, the factor is the ratio, so it should be the response of propane, the specific response for propane. Our main point here is that it's only on one publications that define this way, and that it's relative to propane. It's nothing to do with the camera sensitivity, because any bandpass filter between 3.2 to 3.5, doesn't matter what is the NETD of the detector, it doesn't matter what is the transmission, the actual transmission of the filter will give you above threshold values to all relevant compounds. So this is not a criteria for sensitivity of the camera. So therefore, the only purpose it serves, that it's defined the spectral range of the camera to do OGI surveys under the Appendix K. So these are the issues that I'm going to talk about, and I already mentioned the response factor is not a measure of the camera sensitivity. And in the end of this Appendix K, they put Annex 1 out to develop experimentally the response factor. We have 2 points about that. One is all the values of the response factor are easily computed for all compounds that are relevant under this regulation, and they are all above 0.25. The lowest one is for methane, and the other issue is that you don't need an experiment to evaluate. We offered in our comments an alternative method how to measure the true response in much simpler way experimentally if we need any criteria for the camera sensitivity. And in section 3.1.2 over here, the initial detection requirements are too loose because they put 17 grams per hour at 5 degrees delta T, at 2 meters, at 1 meter per second wind speed. This is for methane, 5 for butane, and 18 for propane. Our cooled OGI cameras, every OGI camera is about 100 times more sensitive than these values, and I will show it in a second. And we don't need, once we are starting to develop the envelope of detection, like the envelope of operation, we have a lot of room to develop a wide envelope of room, but a camera that is barely make it to this initial criteria will have a tiny envelope for detection. So essentially, there is no sensitivity requirement under Appendix K for OGI camera. The door is open to a lot of technologies that are much less sensitive. So in order to explain what is the response of the camera and what is the response factor, we're looking at what we call the OGI equation, and this integral over here, it's what we call the compound-specific response of the camera, which is also in the Zhang 2017 paper. We define it in the same way, and you can see that the response is a function of the transmission through the gas plume, and it's a function of the CL through the gas plume. And it's a function of the absorption coefficient and a function of the filter range and transmission. So if you look up here at the image of methane with our standard filter, which is very similar to all OGI between 3.2 to 3.5 micron, you can see there is an overlap for methane and other compounds on the filter, bandpass filter. So if we look at the spectrum at different CL value for methane and propane, you can see the larger the concentration, the larger the CL, you can see the spectrum of the CSR, the integral over all the wavelengths on the filter bandpath. You can see it fills up the filter as the concentration going up. And if you calculate the integral over this spectrum from lambda 1 to lambda 2, you get a value for each concentration. And this is the compound specific response curve. And this is the integral in the OGAL equation, which is the integral from lambda 1 on one side of the filter to the other side of the filter of 1 minus the transmission times the transmission of the filter, the transmission through the gas times the transmission through the filter. And CSR, the response factor, is actually, as defined by Zheng et al. 2017, is the ratio of the CSR of the target compound over the CSR of propane in the case of Appendix K. So if you look at this curve for propane and methane, you can see the CSR curve looks quite differently. This is logarithmic scale. And what you can see, the green curve is actually the response factor. So you can see at 10,000 ppm, it's 0.45 here. Why is it much higher than the 0.3? I will show you in a second. But this is the definition of the response factor. And this has nothing to do with the actual transmission, because it's a ratio. It's a ratio between, so if the actual transmission is 0.5 or 0.8, it will not make a difference on the response factor. And it's all gases that as absorption that overlap these 3.2 to 3.5 will give you values above the 0.25. But the big question is, if this is the response factor for methane over propane, this is the ratio of these two curves in 10,000 ppm, why is it much larger than 0.45? And this led us to a point that I will make in a second. We use this compound response curve, specific response in our quantification. And we actually, in each pixel of the image of the OGI camera, can calculate the concentration very accurately. We did an experiment that we put side by side the camera and a tunable diode laser pointing on this black body. And we can see also a time series in each frame that match up really nicely. And our quantification using the integration, the absolute calibration integration of the response at each pixel, we can get the right conversion to CL, and our accurate determination of CLs compared to the tunable diode laser technology. We can see we have a slope close to 1 and a very high R square. This is second by second, by the way. It's very accurate. We mentioned our previous, we are using this exact pixel concentration CL measurement in our new feature inside the camera to measure the average concentration through the plume on the camera. This is my last, but I want to go back to the response factor. So if I look at two filters here, first of all, in 611, when they define the RF requirement, they say the OGI camera must be sensitive. In the EPA view, RF is connected to sensitivity with a response factor of at least, and it's 0.25 at 10,000 ppm meter. This is the end of this sentence. So what we are showing, this is the blue one is I think it's the GF320 FLIR filter, and this is the OPGAL standard filter. They're essentially the same, and they will produce very similar response factor when we calculate it. So as I said, the response factor is not a measure, it's a relative measure of sensitivity. And if the camera cannot see propane very well, the response factor will be the same, but the sensitivity of all other gases will be much lower. So it's nothing to do with the NATD, it's nothing to do with the filter actual transmission. It will produce the same response factor, it will pass the threshold, but the camera could be much less sensitive. And it can it can also barely get 612, which is the initial criteria for the 17 gram per hour and the 18 gram per hour and the 5 gram per hour for the 3 compounds in Appendix K. So, I'm sorry. So it's only a function, what I'm trying to show over here, it's only a function of the filter range and the absorption coefficient of the gas. And once you have these two variables, you can calculate it. So we know where are the absorption coefficients, it doesn't change, and the filters are over here, and the results of the response factor calculation between these two filters is very negligible. They all pass the 0.25 when you do it right. My next point is the 0.25 is the right number? Because when I showed you my previous calculation, I showed you 0.45 for methane, which is the lowest response factor when I do the calculation. We found out recently that the equation in then is that the equation in exponential natural base exponent for the transmission. In this equation here, 1 minus the transmission, it was exponent based, but they used absorption coefficient curve from PNNL, Pacific Northwest Research Laboratory, and all of these spectra of absorption coefficient, absorbance spectra, are 10 based. So at the beginning, I thought it doesn't matter because it's a ratio, but we found out it's really critical to calculate the response factor using the integral here, the summation in a 10 base. If you use an exponent, you have a ratio of 0.25. So we offered to EPA to add to Appendix K a way to calculate, not measure the response factor, and this is a very simple equation. And if you use absorption coefficient curves that were taken in FTIR in a 10 base logarithmic, you cannot calculate the transmission in exponential, in natural base. So you need to match the base, otherwise. So on the left side, we calculate for the same compound, you see methane, ethylene, propylene, ethane, and butane, benzene. We calculated with our standard filter the response factor on the left side, and we compared it to what's in then 2017. And you can see you get the same pattern on both of them. The difference is not very critical, but the pattern here is showing up. This is up. If I click over here, I will do it. I expand here, it's up to 300,000. I expand it to up to 50,000, and it's a similar pattern for all compounds. But what you can see on the OPGAL standard filter, so it's produced the same pattern, everything showing up much earlier. The pattern values showing here at 4,000, and here it's showing up at 10,000, which is the ratio of 2.3, which is log 10 of E, or log E of 10, I don't remember, but the ratio between the two bases is 2.3. So it's just showing up earlier. So the true response factor for methane is around 0.45 right here. What they got in their paper is 0.297, and EPA based on this value, the threshold of 0.25. So the threshold should be higher because all compounds can easily pass the 0.25 when they do the calculation of Another thing we did for propylene, we calculated 10 based and we took the graph and they had a measurement for propylene over there. So if they did, and they didn't get over there a match between their measurement and their calculation, and they couldn't explain it, why the method 2 calculation that took the natural base gave them something that's showing up much later at a ratio of 2.3 in the curve. When I did the same, I took the same calculation with the FLIR, same filter. I did the calculation, I got the red curve that matched their measurement very nicely. So this is like a proof that their measurement was right, but their calculation is wrong. And the conclusion of that all the graphs in that paper are wrong graph of RF calculations. So we, in our comments, and by the way, I add a link over there in my presentation to our comments on the docket of EPA of the regulation.gov. And we also offered a way to measure the actual response, and you can use one black body and one cell of the target compound. And the idea is to do the same type of measurement of 1% of pixel of the image and try, but instead of looking at the ratio between the target compound and the reference compound, we offer to change the temperature and find out what is the threshold of the standard deviation is much smaller than the difference between the radiances between the black body and through the gas cell. This is a way that we can define a delta T, and this is really define the sensitivity of the camera. This is a proposal. It will not be in this round of Appendix K. We talked about to do it in a later updates of Appendix K to find a way to have a better sensitivity requirement for Appendix K. So this is about 612, what I'm showing here on different filters for methane and butane. You can see here that at 5 degrees over here, this is our detection limits as a function of delta T. You can see that we are at the range of 0.1 to 0.17 for each compound, which is a 2 orders of magnitudes better detection at 5 degrees delta T and very low wind speed. So any cool camera, it doesn't matter which manufacturer, will have a large range of envelope, a large envelope of operation when they use the OGI camera. But as it's written right now, anything that pass barely, instead of 1710 gram per hour, not 0.1 gram per hour, will have once the winds start blowing faster than 1 meter per second, you go a longer distance, you have a delta T of 2 degrees instead of 5 degrees, that will have a tiny envelope. It will not detect the 17 gram per hour of methane, 18 gram per hour of propane. So this is another issue that we have between 611, which is the RF requirement, and 612, which is the initial detection requirement. There is no sensitivity requirement under Appendix K. So the door is open to lower grade technologies that actually in most conditions will not detect anything. Okay, I reached the conclusion here. So I just want to iterate that we objected also in the first round to RF as a criteria, but we were explained by EPA, which it's only criteria for the spectral range. They just want to make sure, without saying it, that the camera will be in the MWIR area between 3.2 to 3.5. And what we found out that the response factor is always above 0.40, actually 0.35, to any of these compounds that are relevant. All the VOCs, BTEX values, methane, all of these alkenes will have a larger 10,000 ppm than the threshold value. So we don't see, all you need to know is the range of the filter and you know that you're fine. We don't see any need for this cumbersome experimental development of RF every time the mixtures change. And all these results can be easily calculated. We propose to add to Appendix K a protocol how to calculate it, and EPA may be adding this in the final version. And we also offered maybe making some changes to the initial criteria for detection, maybe lower the temperature difference, making the wind speed larger, because this way the door is open to low-grade technologies. Any questions?
Thank you, Ram. Are there any questions from anybody in the audience? Yeah, there's one.
You're referring to lower grade technologies, but at the same time, it allows you to, for example, detect the leak at the 17 gram per hour at a further distance. So if you're trying to see an emission that's 4 meters away, you can still do that with the current criteria, whereas if you tightened it up, you wouldn't be able to. So just wondering what his thoughts are.
Did you hear that, Ram?
Yeah, I heard it. Yeah, but let's say in 2 meters and 5 degrees and 1 meter per second wind speed, you can see even 5 gram per hour. But once the wind blows 3 meters per second, it's going exponentially lower, the detection limit. So it's way above. You will not see the 7. You understand what I'm saying? Or the temperature difference go below 5 degrees to 3 degrees to 2 degrees, then you will not see. So the whole idea of the envelope of operation, that you need to document how you develop it. And once they start to develop around these cameras an envelope, if the wind will be, instead of 1 meter per second, 3 meter per second, they cannot use the camera for the LDAR survey. Or if they don't have delta T's that are sufficient, they will not see the 17, 18, they will not see the kilogram sometimes. So our mainstream OGI cool cameras can see 100 times better than this initial criteria in these conditions. 100 times, okay? So somehow there is no, RF is not a sensitivity criterion, and this one is very loose. So there is nothing to prevent lower grade cameras that can barely make this initial criteria to get into Appendix K.
Any other questions? Go ahead, Yoshing.
Comment about the statement about the response factor. I agree, response factor is a relative. It's about the same camera, but for different gases. So for certain gases that has a broader band of absorption spectrum characteristics, the difference may not be that big, but for other compounds, when your spectrum window is kind of borderline across a particular compound, then it can be quite different. I'm just making that comment. And for certain, I don't know EPA's intention, but I can tell you that they're probably trying to say if your camera is sensitive enough to measure whatever the compound or gas you're using for calibration or to verify or as a verification, that may or may not be suitable for other gas. I think that really the purpose of the response factor is about different gas. It's not the camera, and camera sensitivity is covered by other part of Appendix K.
Which part? I should ask you.
Well,
Which part?
their detection, I'm not the EPA writing that, but my understanding that they have their way to say, okay, in order to be able to adequately detect the gas, you have to meet those criteria. So that's where they have it.
As it written, let me answer you, Shane.
Go ahead.
Okay, so the other part, there is no requirements in the current appendix proposal, Appendix K proposal. There is no requirement for the size of the envelope of operation, and the 17 gram per hour at 5 degrees with no wind at 2 meters is very loose. That's what I'm saying. It's very, very loose, and so there is no other sensitivity requirement in the old document. So I agree with you that there are some unique that may have lower than the methane response factor. But you tell me, do you think they based the 0.25 value based on the methane calculation? Why did you choose 0.25? Because it's very close to the methane calculation, am I right?
I cannot
Yeah,
tell you what's there.
Yeah, we don't, unfortunately, we don't have the EPA in here right now, Ram.
Yeah,
to
okay,
clarify
okay.
that. But what we can say is through your research with your specific filter that is a little different than the FLIR filter, the Sierra
No, no,
Olympic filter. Hang on,
I
Ram.
use the FLIR filter. I use the FLIR filter for this calculation, and I got same results. But when I did the exponent base, but when I did the 10 base, I got different results that matched the experiment that Zeng et al. Did.
Okay.
So
Yeah,
I used so you know, it says in the paper they use the PNNL. The PNNL is a 10 base absorption, and they did in their calculation exponential, and that's why they got different results. The difference between the filters is very insignificant. As long as the filter is between 3.2 to 3.5, it will give you almost the same response factor for all compounds if you
So
do the calculation right.
Your main argument is just you don't like the 2.5, you want the 0.4.
I'm saying if they use,
Are you choosing 0.4 solely because the Zeng et al. Paper chose 0.297? I'll kind of throw it
No,
back to what
they didn't
you asked
choose.
him, why they use 0.25. Are you using
No.
0.4 solely because of to contradict that the peer-reviewed paper?
No, it's not that I got a different result. I got the same result that he got when I did the calculation the same way he did. With the same filter, the same equation that he used in his paper, I got the same result. There is no mistake. He just used an exponential base. And this is not, all I'm saying, people who are doing these calculations need to pay attention to the base of the absorption coefficient or the reference library that they use to do this transmission calculation in this ratio. If they don't pay attention, they will get the wrong results. That's what I'm saying. And I'm saying if EPA based the 0.25 on this 0.3 in this paper, they need to reconsider this value because typically it should be higher, because when they do the calculation right, they need to get higher numbers.
But the higher number does not match the experiment.
No, it matched the experiments very well. This is the propylene number. When I did the same, I used this red one, okay? This red one is a 10 base calculation of response factor with a FLIR filter that I took from the paper. And this is the black squares are the measurement in the papers. I took it from the table and I put it, and it's match my calculation match your experiment better than your calculation to your experiment. That's what I'm showing here. Because there is a
right place to make those kind of discussion or argument, but you are picking a different compound here. Your argument is about methane. Here you are talking about, so I don't know. I think we can, out of this this kind of venue, we can have a deeper discussion. But here I just, without actually revisiting some of those. What about the comparison specifically on, because the argument is about the methane, then why don't you go back to methane? If you go back to methane, does that match the experimental result too?
Better than your, yeah, better than yours. Yeah, it matches better than yours. But I didn't do it for all compounds, but all I'm trying to show is the point. When this black curve that I got over here is my calculation natural base, and it's exactly the same like your calculation.
I think, like I said, I don't know how critical this argument is, but I agree with this principle. The response factor is about the different chemical species, not about the camera itself. So if you want to convey that to EPA, I support that argument. And EPA should consider that. And for the same camera dealing with different gas material, you should consider. Basically, this approach is very similar to EPA's current method 21. In method 21, they have Appendix D that has all kind of response factor for different instruments. So basically, it's the same idea. That's why that has the response factor. Even the word is the same as response factor in Appendix D of the EPA protocol.
Yeah, but you use the same wording and it's taking, but it's a different technology. It's a different technology. And all I'm trying to say, it's about the compounds. I agree with you. All I'm trying to say that all of these compounds that are relevant out in this regulation will pass this. When you have a filter between 3.2 to 3.5, it will have very similar response factor. It doesn't matter if it's the OPGAL filter or the FLIR filter. You get very similar results because that's where the compounds are. And you can easily, you agree with me, Yushen, that you can easily calculate it. Why going for this very tedious experimental require this?
That's why we have method 2 in our end of paper. We actually recommended that. And so it's a EPS choice to which one.
Yeah.
So it's not really, if you want to ask that question, I think you should ask EPA. It's not about the author of this paper. Another point is when you say, I agree, a large number of compound probably is in that filter window, that's fine. And one thing that comes to my mind is benzene may not be as easily because it's on the edge of that. If you shift that, it may not be the same thing.
Benzene, if it's benzene is on the edge, I know, but it's around 3.2. But we know, we calculate the benzene. Okay, what Yushen, we can take this discussion to a different venue. I agree with you, but I want to pay attention to this. My comments in the dockets in this link, and you can download, and everything that I just showed you is written very clearly over there. If you want to go and look.
It's always exciting to get to hear you and Yoshing talk above everybody else in the room. So no, we appreciate your time, and I know it's probably middle of the night over there, so appreciate you taking the unique time out of your night versus day to join us here at the conference. And yeah, this sounds like this may be a conversation to continue. So thank you.
Thank you, Shane. Thank you, everybody. נסתכל על זה, שאני לא יראו אותי לפני שאני מקלל אותו.